Hello, good afternoon. Sorry for my delay. Okay, so let's start the tutorial now. Let me maximize the slides. Okay. So today's tutorial will be about the solution of homework 3. An announcement. So we will be giving you homework 4 today. Okay, so let's go back to the solution of homework 3. In this assignment, we have 5 questions. Only question 1 and 3 are something that is not routine. So for all the remaining questions, so they are just exercises to test your understanding. So I will make everything very brief. Okay, question 1. Question 1 defines something called a derangement. We have the integers 1, 2, 3 up to n. We can form permutations of these numbers. And the derangement is a permutation such that every item, so every one of these numbers is not staying at its original position. So for instance, when n is equal to 3, we are looking at permutations of 3 numbers. Now, 2, 3, 1 is a derangement because 2 is not at the location 2, 3 is not at location 3, 1 is not at location 1. And similarly, 3, 1, 2 is also a derangement. But 1, 2, 3 is not. 1 stays, right? 1, 3, 2 is not because 1 stays. 2, 1, 3 is not because 3 stays. And 3, 2, 1 is not because 2 stays. Is that okay? So in that sense, out of the 3 factorial permutations, we find that 2 of them are derangements, and then 4 of them are not derangements. Okay? Our idea, okay, or our target here is to find out how many derangements are there for general n. We let dn to indicate the number of derangements among all n factorial permutations. We want to get the recurrence relationship of dn with the former terms. Now what we can see is here. In order to get a derangement, we can separate the discussion into 2 disjoint cases. Case 1 is, so because we want to have a derangement, so 1 is going to be mapped to some position. Let's say 1 is not going to stay at location 1, but it is going to stay at some other location, let's say x. But then the number x itself, in case 1, it goes back to 1. So it is like x and 1, these 2 numbers are swapping positions. So how many ways are there? So once, there is a mistake here. So once x and 1, they swapped positions, then what we need to care is about all the remaining items. Every one of them should not be staying at their original position. So the number of ways will be, so 1 and x already swapped. So the remaining, we have n minus 2 items. So the number of ways is d of n minus 2. Now, the choice of x here, there are n minus 1 choice. So the number of ways that we can have case 1 is, so there is a typo. So there's something, these 2 should be switched. The number of ways that we have case 1 is n minus 1 multiplied with dn minus 2. Is that okay? Now, for case 2, 1 goes to x, x goes to something that is not equal to 1. So in that sense, we can think of this 1 and x as some label merged together. Let's call it a big Y. So what we are looking for is y should go to some other number other than 1, right? And all the other numbers should not go to itself, and the last number will go back to y. So in that sense, we are merging x and 1 together so that we are looking at only n minus 1 effective numbers instead of the original n numbers. So in that case, if 1 goes to a particular x and x goes to some other number, the number of ways that we can have is dn minus 1. But there are n minus 1 choice for this x that we can use. So the number of ways is n minus 1 times dn minus 1 ways. So using this combinatorial argument, so notice that we don't have any formula for dn minus 1, dn minus 2, or whatever. We are arguing this to be correct combinatorially. Based on these combinatorial arguments, we find out that d of n is equal to n minus 1 times dn minus 1 plus dn minus 2. Okay, so this is the first part that we want to ask you about question 1. So here in this recurrence, dn is dependent on both the two former values, dn minus 1 and dn minus 2. But actually, we can make a further simplification. Let's see what happens below. Now, by rearranging the terms, so I'm going to move this n times dn minus 1 to the left-hand side. So I want to make it into dn minus n times dn minus 1. So what is left will be minus of dn minus 1 plus n minus 1 times dn minus 2. Is that okay? Now, if you look at this part is the same as this form, except that we will replace n by n minus 1, replace n by n minus 1, and plus becomes minus, and minus becomes plus. So it is like we are multiplying minus 1 to this one, but then make n smaller by one value. If this is the case, then we can see that we can continue to do the next step. So we multiply everything by minus 1, but then we also make n smaller by one term. So we get dn minus 2 minus n minus 2 times dn minus 2. So if we go on like this, then eventually we will get minus 1 to the power n minus 2. So this counts the number of times that we have the minus 1 multiplied. And then we will have d2 minus d1. Now, what is d2? d2 is the number of derangement when you have exactly two terms. So the number of derangement is there is only one. So d2 is equal to 1. And d1 is 0 because there is no way to get a derangement if you just have one item. So that means that d2 is 1, d1 is 0. Is that okay? And then minus 1 to the power n minus 2, we can write it in a simpler term. It is exactly the same as minus 1 to the power n because we will multiply minus 1 and minus 1. So we multiply 1 here. So this is 1. This is minus 1 to the power n. Is that okay? So we get dn minus n times dn minus 1 is equal to minus 1 to the power n. So this is what we get. So in this formula, or in this recurrence relationship, dn is only dependent on the former term, dn minus 1. Okay, so this is question number 1. Question number 2 is a standard recurrence relation problem. We want to solve it. So we can use the method described in the lecture. You can also use your own method, but I think the method described in the lecture is the easiest one. What we are going to do is we want to find out the particular solution for this one and also to find out the homogeneous solution. Combining these two, we will get the solution. Okay, so how about particular solution? Now, because the formula is of the form AR blah 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 is equal to 2 to the power R, so it is natural to assume that AR looks like 2 to the power R. We are guessing AR is of the form some constant K multiplied with 2 to the power R. So in that sense, if AR is of the form like this, so we plug in the equation, this is AR, this is minus 6 times AR minus 1, this is plus 8 times AR minus 2, it is equal to 2 to the power R. So after simplifying the terms and then solving the equation, we will get K, big K is equal to 1. So AR is equal to 1 times 2 to the power R is a particular solution. So this particular solution fits in this recurrence. But then it may not be the correct one because we may have initial conditions to consider. So in that sense, we need to find out the homogeneous solution. Okay, now for homogeneous solution, we can solve it by writing down the characteristic equation, so which is equal to x squared minus 6x plus 8 is equal to 0. Now for this one, we can find out that the roots are 2 and 4. So the homogeneous solution will be of the form a constant multiplied with the first root to the power r plus another constant b multiplied with the second root to the power r. Okay, so this is a homogeneous solution. Combining with the particular solution, we get the total solution of this form. So this is the particular solution, and this is the homogeneous part. Now, once we know that it is of this form, we can now go back to take a look of the initial values. So A0 is equal to 2, A1 is equal to 10. By plugging in the initial values, we have A0 is equal to 2. So when R is equal to 0, we have an equation. 2 is equal to 1 plus A plus B. And when R is equal to 1, we will have another equation. 10 is equal to 2 plus 2A plus 4B. So in that sense, we will have two equations allowing us to solve for the two unknown constant A and B. So we can find out what is A and what is B, and that's it. Okay. So this is so once A and B are known, so we get the total solution. Now let's do another exercise again. So this time we have AR minus 5 AR minus 1 plus 3 AR minus 2 plus 9 AR minus 3 is equal to 0. Something that is super nice here is that we immediately can tell 0 is a particular solution. So we write down 0, okay, for the particular solution. If we can find out the homogeneous solution, that will be the answer, because the total solution is 0, the particular solution, plus the homogeneous one. Okay, so we focus on solving the homogeneous solution. So again, this time, we look for the characteristic equation, which is x cubed minus 5x squared plus 3x plus 9 is equal to 0. And by some trial and error, we will quickly find out that, oh, minus 1 is a root. And then after you get minus 1 is a root, the formula will become, so after doing this, factorization, we will find out that this is equal to x plus 1 multiplied with x squared minus 6x plus 9. And the latter part is equal to x minus 3 squared. So we will find that the roots are minus 1, and then 3, and then another 3. So 3 is a double root. Now the homogeneous solution will be of this form. A constant times the first root to the power r plus a constant multiply r plus another constant together multiply with this root to the power r. It is because of double root, so we will have this form, br plus c instead of a single constant. Okay? What is next is we solve for this one. This time we have three unknowns in the total solution, big A, big B, big C. So this corresponds to having three initial values. So if we have three initial values, 0, A0, A1, and A2, then we will have three corresponding equations allowing us to solve A, B, C. So after solving it, we find that A is equal to 2, B is equal to 1, C is equal to 5. So in that case, AR is equal to 2 times minus 1 to the power R plus R plus 5 together multiplied with 3 to the power R. So once you have done this, actually a good habit is to double check whether your answer is correct. If this equation is correct, then you plug in R is equal to 0, you get 7. You plug in R is equal to 1, you should get 16. And you plug in R is equal to 2, you should get 65. This is allowing you to check, double check whether you have any mistakes in the calculation. Okay, the third question. Okay, so the third question is a recurrence, not in the standard form. It is not a linear recurrence. So the recurrence is of the form AR squared minus 2 times AR minus 1 squared is equal to 1. But there is a hint. The hint is BR is equal to AR squared. We can set BR to be something like this. So suddenly, this original recurrence will now become a linear recurrence. We get BR minus 1 is equal to 1. We just solve for it. Solve for BR, and then we go back and check what is AR. Okay? So we can solve for BR and find out that the total solution is actually equal to R plus A of this form for some constant A. And because the initial value of A0 is equal to 2, A0 is 2 in the assignment, in the question, but when A0 is 2, then B0 will be 4. Okay? So we actually get the initial value of B0 is equal to 4. So by plugging in R is equal to 0, then we know that this big A should be 4. So in that sense, BR, after evaluation, we will get BR is equal to R plus 4. And originally, AR squared is equal to BR, so that AR is equal to square root of R plus 4. Now notice that AR could be equal to the minus of the square root of R plus 4. But we can see that this is not correct because A0 is equal to 2. So we know that the answer for AR is the plus part of the square root. So AR is the plus of the square root of R plus 4. Okay? So question 3 is tricky. We have another question. So question 3b, I forget. So the ordering is like this. So this should go first. So we want to solve for this recurrence. Okay. AR square minus 2AR minus 1 is equal to 0. Now we get into a trouble. This is AR square, but this is only AR minus 1. So we cannot use BR to represent AR square, because in that sense, this will be the square root of BR minus 1. But luckily, this is equal to 0. So let's see what happens if we do the rearrangement of terms. So when we move this to the right-hand side, we will have AR square is equal to 2 times AR minus 1. Still not okay, but then we can see that we can take log base 2. So let's take log base 2. So when we take log base 2, so we will get 2 times log of AR is equal to 1 plus log of AR minus 1. So great. So what should we do? Let's call this BR. Let's call this BR minus 1, right? So we set BR to be equal to log of AR. The base is 2, okay? So in that sense, the previous equation here is becoming 2 times BR is equal to 1 plus BR minus 1. So again, we get the linear recurrence. So for this linear recurrence, we can solve for the total solution. The total solution will be equal to BR is equal to 1 plus A times 1 over 2 to the power R. Okay, so here, we should also find out what is the particular solution. So we will see that 1 is a particular solution. Is that okay? So when BR is equal to 1, 2 times 1 is equal to 1 plus 1. So this is actually, this one represents the particular solution. And then the homogeneous solution is of the form A times 1 over 2 to the power R. So now we have the form for BR. So let's solve for BR completely, because we don't know what is this big A. So to solve for this big A, what we need to do is we go back to the initial condition. So the initial value of A0 is equal to 4. When A0 is equal to 4, B0 must be 2. Is that okay? So B0 is 2. After doing plugging it, we will find out that A is equal to 1. So in that sense, BR is equal to 1 plus 1 over 2 to the power R. And AR is equal to 2 to the power 1 plus 1 over 2 to the power R. So you can verify whether this is correct by yourself. Notice that I may make mistakes. So I'm making these slides very in a hurry. So I may make bad calculations. But you can try and see if it works. Okay? So this is the high level idea. Okay, now question 4a is another type of standard assignment question. So for this one, we have a recurrence relationship, and we want to get the corresponding generating function of the terms A of R. So we let AX to be the generating function for the terms A0, A1, A2, and the relationship of this AR is like this. So this is like a brute force or a brute force procedure. So imagine we are going to list out all the equations that we have for this one. So we will list out A2 minus 5A1 is equal to 6 plus 6 is equal to 0. This is one equation. Another is about R is equal to 3. A3 minus 5A2 plus 6A1 is equal to 0, and so on and so forth. And we add everything up. So when we add everything up to infinity, we will find that what corresponds to this term. Okay. So we were not just adding things up. Okay, so for this one, when R is equal to 2, we will multiply the equation by x to the power 2. When R is equal to 3, we will multiply the equation by x to the power 3, and so on and so forth before we do the adding. And then when we add everything together, we will see that corresponding to AR, we have AR x to the power R. So we will get the terms related or inside A of x. So in that sense, when we add things up here, we should get something that is related to A of x. So in particular, we will get A of x minus A1x minus A0. Is that okay? So this is by adding up this part. And similarly, when we add up this part, we will get minus 5x multiplied with ax minus 6. Is that okay? And when we add up this part, we will get plus 6x squared multiplied with ax. Now for this assignment question, we just ask you to find out what is the generating function for ax. So, okay, that's easy. When we have this one already, we can rearrange the terms and find out what is ax. So it turns out that this is minus 5x, this is minus 6, so it cancels with this minus 30x. So in that sense, the only remaining part is minus 6. This is not related to ax. So moving it to the right hand side, it is plus 6. So we have a 6 here. And what we need to divide is 1 minus 5x plus 6x squared. So we get this one. Is that okay? Again, my calculations may be wrong. But this is the high-level idea, how it works. So you can work out the generating function by yourself. Similarly, we have question 4b. So this time, it is slightly more complicated. We have this part, but it is not like equal to 0. We will have 4 to the power r plus 6 on the right-hand side. But we do the same thing as before. We list out all the equations that we have. So this is the equation that we have. So for AR, the equation, we are going to multiply this with x to the power r. So in that sense, summing up all the terms due to this AR, we will get AX minus 60x minus 20. So this is minus A1x minus A0. Is that okay? And for all the terms related to this one, it is going to be minus 2x multiplied with AX minus 20. And finally, for this one, if we add up everything, we will get minus 3x squared multiplied with ax. So we are done with the multiplication and the summation of the left-hand side. And how about the right-hand side? So remember, we are going to multiply this one, 4 to the power r plus 6, by x to the power r. So in general, we will have 4 to the power r, x to the power r due to this term, but we start the terms counting when r is equal to 2. So when r is equal to 2, the first term that we have will be 16x squared. So we will have 16x squared as the first term, and then for each term that we add onward, it is 4x of the previous terms. So the summation of them will be 16x squared divided by 1 minus 4x. And similarly, for this sixth part, the first term will be 6 times x squared, and then for each term onward, it will be x times the original part. So it is going to add up to 6x squared divided by 1 minus x. So that's it. So after rearrangement of terms, we will get ax. So I will not do this for you. This is just a simple algebra task. Okay, finally, this is question 5. Question 5 is also a standard thing to test your understanding about the lecture materials. So this time we let Bn to be the number of n-bit binary strings where 01001 occurs at the nth position. And then for this question, we want to find out, what is the generating function for these terms B0, B1? But before we find out the generating function, let us get the recurrence first to get the idea what Bn should be related. Now we consider, how do we do? We consider all the strings that ends with 01001 that are n bits long. Because the ending part is fixed, 01001, so the number of these kind of strings is 2 to the power n minus 5. There are these many strings ending with 01001. But not all of the strings belongs to this type that occurs at the nth position. Bn of them, of course, they should be counted. But why don't we have all the strings counted as ending at the nth position, occurring at the nth position? Because there could be the case that a string that has 01001 ending at this location. So in that sense, out of all the 2 to the power n minus 5 strings, some of them are ending at the nth position, and some of them are ending at the n minus 3 position. So in that sense, these two add up to 2 to the power n minus 5. And now we can do the standard thing that we have. So we sum up everything. So we multiply this with x to the power n, and sum up everything. So due to this Bn, we should get bx minus b2x squared minus b1x minus b0. So we should get something like this. b2 and b1, undoubtedly, we can set them to be 0 because the string of length less than 5 cannot have any 0, 1, 0, 0, 1 to occur. But on the other hand, we intentionally set b0 to be 1 because we want to apply the result that is discussed in the lecture notes. So we will set b0 to be 1. So in that sense, the summation due to this bn term, we will have bx minus 1. And the summation of this one due to this bn minus 3 terms, we will have x cubed multiplied with bx. And the summation of terms like this. So if you look at this, when n is equal to, so what is the first term that we have? We are going to add things when n is equal to 3, right? So when n is equal to 3, then we will have what? We will have 2 to the power, minus 2. So it is going to be divided by 4, okay? So the first term is actually equal to 1 over 4, that we see. There is a bug here. So the first term is 1 over 4 multiplied with x cubed. Okay, when n is equal to 3, it is going to be 1 over 4 multiplied with x cubed. So this is the first term. But for all the other terms that we go on, it is 2x times the previous one. So we get a generating function of something like, this should be a 4 here. Okay, this should be a 4 here. So somehow the high level idea is we will have a relationship of bx allowing us to get the generating function of bx in terms of x. So this is wrong because of this mistake here. So I will correct it. But this is the high level idea. Now, once we know the bx, then it facilitates us to solve the next part. The next part of this question is we define C of n to be the number of n-bit binary strings such that 01001 first occurs at nth position. Now, this is something different from occurring at the nth position. This is the first occurrence, has to be at the nth position. Again, we let Cx to be the corresponding generating function. And based on the lecture notes, okay, because we set B0 cleverly, then in that case, we can write down the relationship between Cx and Bx in this way. Bx minus 1 will be equal to Cx multiplied by Bx. So we rearrange the terms, we will see that C of x is equal to what? We divide Bx on both sides. C of x is equal to 1 minus 1 over Bx. So if we have Bx of the form like this, then it is very easy to get 1 over Bx. We just turn this denominator and numerator upside down. Okay, so that's actually all that I want to present for today. So sorry for the mistakes again. So I will make the corrections and then send to you after this tutorial. Okay. Okay, thank you very much. Okay, remember we will have assignment homework sent to you today. Sure, Q of 2A. Let me see. Question 2A. Let me go back. Okay, so question 2A here. So this is the solving of recurrence. So the standard way that we are teaching in the class is we find a particular solution and find a homogeneous solution. So particular solution is very easy because we can observe the terms that we will have in general. So if AR blah 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 is looking at something like 2 to the power r in the end, so AR, a natural guess is AR looks like some constant multiplied with 2 to the power r. Now, if we guess AR is equal to this one, then in that case, this is k times 2 to the power r, this is k times 2 to the power r minus 1, this is k times 2 to the power r minus 2. So in that sense, we can solve for k. When we solve for k, then we get AR, a particular solution, is just 1 times 2 to the power r. Okay, we will remember this. And the next part is we want to solve for the homogeneous solution. So this part, we can rely on the characteristic equation method. So the original recurrence is this one. Homogeneous one, we want to set it to 0 because we look for the cases where how AR will make things 0. The characteristic equation will be something like x to the power 2 minus 6x plus 8 is equal to 0. So once we have this one, we can find the roots. The roots will be 2 and 4 because it is x minus 2 times x minus 4. This is like this. And characteristic equation tell us the root, and the roots tell us the homogeneous solution, how it looks like. It will be of some constant multiplied with 2 to the power r plus some other constant multiplied with 4 to the power r. And after that, total solution is simply the particular solution plus the homogeneous solution. So if you just put this into the first part, then it is always working. But now we have initial values given as well. So when we have initial values 2 and 10, then we cannot have any A, we cannot have any B to be written here. When we have the initial values, in that sense, we will have corresponding equations. A0 is equal to 2 to the power 0 plus this one plus A times 2 to the power 0 plus B times 2 to the power 0. So we will have A0 is equal to 2. We will have an equation 2 is equal to something in terms of A and B. We will also have another equation 10 is equal to something in terms of A and B. And after solving for A and B, we will get big A is equal to minus 2, big B is equal to 3. So in that sense, we will find out AR is equal to 2 to the power R plus minus 2 of 2 to the power R plus 3 of 4 to the power R. And this total solution will not just satisfy the original recurrence. So it will satisfy this recurrence, but it will also satisfy the initial condition A0 is equal to 2 and A1 is equal to 10 at the same time. So this is how we can solve a recurrence like this. Okay? Let me see. Oh, k is equal to 0. Oh, maybe. So thank you very much. Maybe I'm making a mistake. So I'm doing things very quickly. Maybe you are correct. So if k is equal to 0, then it is 0. Okay? So I will make corrections after the class. Is that okay? Is this 0? Let me double check. Oh, yes, it is 0. Yes, I make a mistake. That's true. Is it 0? No. Let me see. Is it 0 or not? Yes or no? Maybe you're right. Let me see. Maybe you're right. Let me see. 1 plus. Oh, thank you very much. It should be 0. Yeah, I make a mistake. I make a mistake that 8 divided by. Thank you very much. 8 divided by 4 is equal to 2. It should be the correct way, right? So somehow I get 8 divided by 4 is equal to 4, something like this. Okay, thank you very much. So I will make corrections. Okay? Okay, so see you again. Yeah, I'm really sorry for the mistake. Yeah, so, okay, are there any other questions? So, k is equal to 0. Let me double check. So I will give you. Yeah. Oh, I see. Okay. I will make corrections. Thank you very much. Yeah, that's the problem. Yeah. Okay. Thank you.